All right, so everybody take a peek at the inspirational quote for today.
That ain't no quote.
That's a quote right there.
That ain't no quote. Okay.
Stare at it for a second, and then we're gonna have Daphne explain it to us.
Damn, Daphne.
Everybody just look at it and let it soak it in. Reflect on that. 'Cause that's not math. That's more spiritual. Yeah? It's kind of deep. Wait for it. Wait for it. Daphne, what do you think?
One will always be one.
Oh.
Okay.
Well, can you give us a hint?
So, here's your hint. 365.
365 days.
Yeah. Andrew, what do you think?
Alright, so like it shows that like alright, it's 365 like represents like good days, like, every day of the year.
Mm-hmm.
And I guess like the top's like 0.01, it's only up like by 1 or 0.01, I'm sorry, like it's
Like 1% more.
yeah, it's like only 1%
bit
more,
more.
and it makes all the difference because that's 37, like 37.78, and then take one out, it's all the way to 0.026. So I guess
What does that mean?
So I guess
No, this isn't calculus.
what is it? Yeah, like it just shows like every day, like every little thing can matter, like every day. That's what I'm thinking.
Yeah, Janice, what do you think?
If you like percentages, if you give your 99%, you get that much more work. You do 100%, you get 101%, you get that.
Yeah, think about it like percents. So if I just do like what I can do every single day for the whole year, I might not change, nothing may change. It may just like, yeah, I did, whatever I needed to do, did the minimum, I did my thing. But if I give a little bit more, just a little bit, extra time, extra effort, extra thought, just a little bit more every single day, and it's not, not a whole lot more, just a little bit more every single day, I get this number here. If I give a little bit less every single day, like, whatever, cut some corners, take some shortcuts, whatever, somebody else will do it, you know what I mean? To do a little bit less every day, I get this number. Look at the difference between these two numbers. Huge. Right, at 211 degrees, what can you tell me about water? At 211 degrees.
It evaporates.
No.
Fahrenheit, Celsius.
Fahrenheit.
Oh,
At 211 degrees, you have hot water.
Yeah.
At 212 degrees, what happens?
Hot water.
Yes. It evaporates. It changes its entire state of being. Right? It goes from a liquid to a gas. It becomes a different phase of water. And then steam can power a locomotive. Right? Steam is what's capable of powering, thousands of tons of heavy machinery along this road across the entire country, right? So that 1 degree makes all the difference. So a little bit more. And so that's what I'm going to encourage you all to do, is just give a little bit more every single day. It doesn't have to be a whole lot, but every day, push yourself a little bit further outside of your comfort zone. Just do a little bit more than what you thought you could do. So that's how you get better. That's how you grow. Does that make sense? Right? Like, how about in the gym? Say you're doing a set of 10 reps on the bench. When do you get the most muscle growth? Which rep gives you the most muscle growth? The 12th one. Right? Am I right or am I right? You gotta push yourself. All right. So I'm preaching for today. It's my daily sermon. Okay. Let's do a little bit of review about what we did yesterday. Asia, what was yesterday? What did we do?
We learned the exponential growth.
Oh yeah, the exponential growth formula. Yeah, we took a look at that. And Cecilia, what about the exponential growth? What was that all about? Can you tell me about it a little bit more? You don't have to like give me formulas or any super detailed stuff, but you know, why do we look at it? Who cares? Exponential growth. Woohoo.
Is it like this? As you be wearing like, is it I don't know.
I will say that Albert Einstein called exponential growth the eighth wonder of the world. It's kind of cool. But how about Selena? Can you see the reason why I said let's talk about exponential growth? So I pulled it because it's exponential growth isn't calculus, but there was a reason. There was something we could look at that kind of led us into calculus. Why did I talk about exponential growth? What about a limit? Yeah, E is a limit. Does anyone remember? Can anyone say more about that? About E being a limit of something? Daphne?
As x approaches infinity.
As x approaches infinity.
Yeah.
Okay, that's mathy. That's the answer in a mathematical sense. But in terms of the context of compound interest, say we're investing money. What does E have to do with anything? And what limit? So say what Daphne said, but in context. Christian.
Is that when you're like receiving interest like all the time?
Yeah, continuous interest. So you could do compound interest and get interest monthly, 12 times a year. And you have this n in your formula where n equals 12. But if we say we get interest every day, every hour, every minute, every second, we approach an infinite amount of times when we compound our interest. So there's this thing that's approaching infinity, and as this thing approaches infinity, we see that there's a limit. There's a point where this growth factor in our exponential function, it levels out at this number E. That was 2.718 something, blah, blah, blah. Jack, what else about yesterday? Limit.
Yeah, I think
Yeah? Okay. Anything else that we missed about yesterday? Andrew? Not yet.
We did it? Oh.
Not yet. We're getting there.
Oh, my bad.
We're getting there. That's today.
We talked about it like in the beginning.
Yeah. We're getting there. Yes, Selena. Okay, yeah. We were looking at limits. Somebody add to that. Alessandra? The ways to find limits. What were some of the different ways that we could find limits? Anybody remember? Leslie? Graphically, we could find the limit. What else, Jenny? Direct substitution. You could plug it right into that thing. Christian, what else? Numerically, we could plug in numbers really, really close to, x equals 5. We plug in 4.9999 and see what we get. Selena? Algebraically, we could do some type of canceling and manipulation. Do some algebra to our thing to find a limit. Okay. So I said yesterday, hey, normally we spend like a week or two, even 2 weeks on limits and blah, blah, blah. So we spent 2 days?
Yeah, 2 days.
Yeah, 2 days, right? So that's really fast. Really, really fast. So I corrected the quizzes, and it looks like we spent 2 days on limits, right? So there's, you guys did fairly well, but there was a few things that, when you're learning super fast, it's usually people need more time to like practice and let it all soak in. And I know you guys have super full days, you're doing stuff all day long. Let's go over the quiz. Let's use the quiz as an opportunity to learn anything that you missed. We can go over it. Hand one of these back to Dewey in the back. How about everyone? Let's all grab a calculator. So, and because part of the stuff on this quiz.
I'll get you one.
Oh, flag on the play.
Bailey or
Give me one, Mom.
So we had an opportunity to learn about limits, and we had an opportunity to learn about calculators. right? And that's a big thing too. You guys thought you were taking the limits quiz. You were actually taking a quiz on calculators, partially, right? Because if you don't know how to use this, it can mess up your answers. So let's all just, well, here's the thing. We can factor this. You can just type it into your y equals exactly as it is. If you want to, you can type in y equals parenthesis. You gotta do this thing, x squared. And now plus 3x. You need to have a minus 10, not a negative 10. Right? Somebody did that yesterday. They used a negative sign instead of a minus sign, and their graph was loco. And then x squared plus x minus 6. And so you can just rely on your calculator to do this. Or we could factor this thing. Factored form, x plus 5, x minus 2, x plus 3, x minus 2. Sweet. So remembering what we know about rational functions. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This isn't. I'm going to have a vertical asymptote where? -3, because this doesn't cancel with anything up top. So at x equals -3, we have an essential discontinuity. We have a quadratic over a quadratic, so my horizontal asymptote will be where? At 1. Y equals 1. We got a horizontal dude. And then there's going to be a hole somewhere. Yeah, x equals 2, there's going to be a hole, but I don't know where. I need to draw the thing first. How about we can have a 0 somewhere? Yeah, at -5, the numerator equals 0. So at -5, we have a 0. Okay, that's helpful. Because that tells me that it's probably going to be one of these jobbies. Like this. Ugh. And then it'll probably do something like this here. And actually, I could probably find a y-intercept. When it crosses the y-axis, x is equal to 0, is it not?
Yes.
Yeah.
So if I plug in x equals 0, all these places are 0. We have 5 times -2 is -10 up top. You with me?
Mm-hmm.
Jenny's? I'm talking quick. 5 times -2, -10 up top. And then 3 times -2, we have -6 in the bottom. So -10 over -6 is 5/3. So what is that, like 1.6? Yeah, 1.6 something. So 1. Okay, so that's my y-intercept. Andrew?
Do you still include the holes, like when you're finding that? Like even though there's a hole, like do you still?
Because the function behaves like this. Actually, if we cancel this and we plug in 0, there's 5/3 right there. That's so silly. You guys see it?
Yeah.
If we cancel this thing out and we just plug in x equals 0, 5/3, that saved the whole time, didn't it? Okay. So this is what's happening mathematically. You type it in your calculator and you have this little screen and it goes ugh. And then you see the difference between here. There's a better understanding of what's happening than you see this. And you're like, what does that mean? So this is why calculators are a useful tool, but you have to interpret it. You have to use it as a tool and say, well, what is really going on? Because your calculator is connecting these lines, even though that's not true. Right? It draws your vertical asymptote, but that's lies. Okay. So does everyone have that graph? Graph that thing. Yeah, it draws the line there. And if you have a weird window, you can hit zoom and then number 6, and it'll give you a standard kind of a 10 by 10 thing happening. And so to answer our questions, we want to approach 0 from the left and right to determine if there's a limit. So we can hit trace and just type 0, enter. And the function is, like we said, it's 5/3 at that place. Do you think it's the same thing from the left as it is from the right? Yeah?
Yes.
Because it's continuous and it's smooth there, and we're like, yeah, that's what's going on. So the limit from the left and the limit from the right are both 5/3. So the limit of this function as x approaches 0 is 5/3, or a lot of people wrote like 1.6 repeat, or something like that. Some people said the limit from the left is 5/3, and the limit from the right is 5/3, and then the limit, and they wrote the limit's like 0 or does not exist or something like that. And I was like, no, you're so close, right? And that's fine. Again, we did limits in 2 days, which is ridiculous. It's fast. But anyway, so that's the limit there. Now if we look at D, E, and F, it says what's the limit this function as we approach 2. So type in the number 2, enter. What's y equal to?
Yeah, I mean, it's nothing.
Nothing. It's not 0, it's nothing. So, remember we said there was a hole there.
Yeah.
So y equals 2. There's a hole in our graph. Right here. So if we want to know what the limit is, we should probably go to 1.9999. Yeah? So type that in. 1.9999. Enter. I got a y value of 1.0000001. What do you think it's approaching?
7/5.
Yeah, 1.4 or 7/5. And if you want to, we could type in 2.00001 and come at it from the right side, right, left side and right side. In order for the limit to exist, the left-hand limit and the right-hand limit have to be equal. Type those in. I got 1.399999999. What do you think it's approaching? 1.4. Yeah? So you should have your left-hand limit and your right-hand limit as we approach 2. Is 7/5 or 1.4 on those. And I was very nice when I graded this. I was very lenient. I was like, yeah. Whatever. Because again, we went through limits super fast. So we ended up with a whole bunch of A's and B's. What next? The limit as we approach -3. What's going on at -3?
So nothing.
Yeah, we have a vertical asymptote. So you could go ahead and type in -2.9999 if you want. But you're going to get a huge number. Let's do it just for funsies. Trace -2.9999. My y value is 200,001. So the y value is, you see what's happening. And I'm going to type in -3.00001. My y value is -1,999,999. Right, so what's the limit?
Or it does not
Does not exceed.
The limit of this function as x approaches -3 does not exist. Right, it's going all over the place. That does not exist. And then J and K, we're saying what is the limit as x approaches infinity? So x is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 100, 1,000. It's going this way forever. What is the y value getting closer and closer and closer to?
1.
You guys see it? Y equals 1 for that. The limit as x goes to infinity. And then as we go to the left, -infinity, forever. What's the y value getting closer and closer to? 1.
The end of the chart.
Yeah. So the limit as x goes to -infinity. Cool. All right, and then the equations for the holes and asymptotes, blah blah blah. People did pretty good on number 2, the bottom section of it. So let's just go through them. So part A, the limit of sine of x. This is sine of x. As x approaches 0, what's the y value approaching? 0. You see it? B, the limit of sine of x as x approaches infinity. What's the y value approaching? It's not approaching anything. Does not exist. The limit, so C, sine of x over x, that's that sinc function. We did this one in class. As x approaches 0, what's the y value approaching? 1, even though there's a hole here. It's approaching 1. The sinc function, sine of x over x, as x approaches infinity, it's approaching 0. Even though it's still got a little wiggle in it. Got a little bit of wiggle. But yeah, it's approaching 0. And then we have E, it says 10 to the x. So that's an exponential function. 10 to the power of x. As x approaches 0, 1, right, 10 to the 0 is 1. And then it says as x approaches negative infinity, so that means go to the left forever. Where is this thing approaching?
0.
It's approaching 0. Sweet. G, so the same thing, as x approaches positive infinity. What's it approaching? It's going to infinity, so yeah, the limit does not exist. And then this one, I was surprised. A lot of people got this one wrong. So the log of x looks like this. Remember, it's the inverse of an exponential, so it's like that, but you know. And I said, hey, as x approaches 0 from the right side, so we're approaching the y-axis. Where is this thing going? Yeah, it's going to negative infinity, so the limit does not exist. So many people put 0 for that one. Yeah, a lot of people. I don't know why. I tried to figure it out. But the limit does not exist on that one. Cool, all right. So if you didn't do as good as you thought you wanted to do on that, don't beat yourself up, right? Most human beings on Earth don't learn limits in 2 days, all right? So it's okay. Just breathe. You're going to live. And it's a learning opportunity. I always learn a lot more when I do stuff wrong and make mistakes. That's when I do my best learning. Right? So if you just do it right all the time and you're not learning, you're just like, I'm fabulous. But when you make mistakes, you're like, oh dang. And then you really think about it and focus on it. It's an opportunity to learn. Okay, now is the day. It's about to go down. You're going to learn the holiest. You're going to learn about the derivative. Yeah, get ready to take some notes. These would be the coolest notes you ever take in your life. If anyone needs any more paper, I have paper up here.
I draw a what a giraffe is. I really don't want to miss it,
Yeah, Marco.
So here are some questions for you. Follow your heart.
Huh?
Follow your heart.
What is this book?
So, Alessandra, the first one, what is the slope of, y equals x, essentially, at the place where x equals 1. So y equals x looks like this here. And she says the slope is 1. Does that sound legit? Yeah, 1x. Rise over run. The slope is 1. You go over 1, up 1, over 1, up 1, over 1, up 1, all day long. So, yeah, the slope is 1. We have a constant rate of change. Constant rate of change. Can I call it ROC? Rate of change. And now how about, maybe I should graph this other one so we get a nice visual. Y equals x squared. One of them there, parabolas. 1, 2, 4. Okay. Christian, what's the slope of that at x equals 1? 1. Would it be? Is it 1? I think so. What does that even mean? Right, because the slope here is, rise over run. But the slope of this, what is there a rise over run? You're saying up from here, we did go over 1, up 1 to get there. But then we went over 1, up 3 more. And then we're probably going to go over 1, up 5 to get to the next point. And over here, actually, we went over 1, down 1 to get here. Right? And we went over 1, down 3. We had a negative slope. And then there was a positive slope. What do you think the slope is at this place here? Anybody?
Yeah.
Slope is 0. There's a negative slope. So this thing has a changing rate of change. That sounds crazy. What should we call it? We'll call it a variable, so we don't have to use the word change twice. Variable rate of change. So I didn't let you know if you were right or not. What even is the... So I give you a hint that, well, first of all, we don't even use the word slope with curves because slope is like a constant rise over run. And then when we have a curvy thing, we could talk about the rate of change of this thing. And we could talk about, we have to talk about the instantaneous rate of change. Because right here, there's a rate of change that's different from right here, from right here, from right here, from right here. There's a changing slope or a varying rate of change all along this curve. And so at this place, our rate of change is going to be the slope of the tangent line. You guys know that word tangent means just touching in one place? Like, here's a little vocab. A secant line is when you have this, and a tangent line is when you have a line that just barely touches it. So a secant line intersects something twice, a tangent line just grazes it. Barely touches it. So the slope of the tangent line, that's going to be our instantaneous rate of change. Instantaneous rate of change. So the slope of the tangent line, instantaneous rate of change. Who cares? Why would we even find that? When am I ever going to use that? So remember we said when we had this parabola, and there was we said that the height function, when we looked at the change in height of something flying through the air, the rate of change of the height became the velocity. So the instantaneous rate of change, and I don't want to scare you with notation yet. I don't want to throw, what this. We'll say change. You guys know delta means change in?
Yeah.
Yeah. So the change in height over change in time, that's going to give us a velocity function. So our instantaneous rate of change of the height gives us a velocity. Now when we look at the change in velocity over change in time, the rate of change of the velocity, what do we get? Acceleration. Yeah, and then, but we could also look at instantaneous rate of change in temperature or change in profit, right? Economics uses calculus to look at profit margins and stuff. There's really anything that's changing, you can use calculus to model it. And what's changing? Everything. Everything in the universe is constantly changing. So, how are we going to find the answer to this question? What is the slope? What is the rate of change of this parabola at that place? We're going to use limits. Duh. You saw that coming. We're going to use limits. So let me deteriorating. Let me draw a better graph and clear this up a little bit. Let's draw. I'm gonna make this look bigger. You know, on the cereal box where it says enlarged to show texture. That's what we're gonna do. I want y'all to see the flavors about to go down. So, if we want to find the rate of change at this place here, we'll call this place x. We want to find the rate of change at some arbitrary place along this function f of x. I can find the rate of change. If I have 2 points, it's easy to find the slope, right? Let me just pick another place here. Yeah, if I have 2 points, rise over run is easy stuff, right? Y'all learn that in probably 3rd grade. Rise over run. It's easy. Let's pick this place here. It's somewhere past x. Can we call it, let's say x plus a thing? We'll say x plus h. Because, I don't know, h. That's why. So x plus a little bit more is going to be some other point that's beyond it. You guys with me?
Yeah.
And then so the height of the function at this place, I bet you is f of x. Alright? We're being general here. And what do you think is the height of the function at this place here?
F of x. F of h.
F of x plus h. Yeah, because this is the x value is this now. So the function evaluated at this place, that's the height of the function. So we could find, we can make a secant line actually. Like this. And that would be, man, I wish I had a yardstick right now. Anyway, so we have this secant line, and it's close to the tangent line is more like this, right? So this secant line is close. It's an approximation, right? This is probably the actual slope. This secant line is a little bit steeper than it. You guys see what I'm talking about? Yeah. Okay. So it's an approximation of the slope of the instantaneous rate of change at this place. So let's just write the slope of this secant line here. What would that be? That would be like a rise over run thing, right? The slope. We'll call that. I'll write this over here. Rise over run is our slope, right? And you may remember when you did your mx plus b stuff, right? You did y2 minus y1 over x2 minus x1. That was like your your rise over run. But so basically we're saying that the change in the y values, so this minus this is my rise. Yeah? So what's that going to be? F of, what's the?
Plus h.
F of x plus h
Minus f of x.
minus f of x
Over x plus h minus x.
over the furthest one minus the closer one. Yeah, that's the slope of the secant line. And look at the bottom here. X plus h minus x. Those x's cancel, right? Yeah. So we're gonna say f of x plus h minus f of x all over h. That's going to be the slope of the secant line. So that's going to be, it's going to be close to the slope here, the instantaneous rate of change here. It'll be close, but it, how close do you want it to be? So here's what I say we do. I say we move these 2 points closer together. If I move this point like here, then the slope is going to be a little more accurate. It's going to intersect here. It'll be closer to so that the actual tangent line might be like this. I don't know, now it's hard to see what the heck is going on here. But you see, as I move this a little bit closer, it's going to be a closer approximation to the actual slope. Yeah? Jackie hanging in there? Yeah? Okay, and then what if I moved it closer? Huh? Will we have a better approximation? That'll be pretty close to this tangent line, right? Then what if I move it really, really close?
I don't know.
Then it's like, well, yes, it's almost a tangent line, right? And if I get them like, 0.0001, like really, really like a molecule to the right, it's basically a tangent line. Right? It's basically, even though it's intersecting at 2 places, those 2 places are so infinitesimally close to each other that it's dang near one place. Yeah? So do you guys see what I'm doing here? I'm doing a limit. Yeah? So what am I doing? I'm making this h be a smaller and smaller and smaller number. So these 2 points are sliding closer and closer together. Yeah? And so we're going to take a limit. Let's do it. We're going to take a limit of we'll say the limit of the secant line as the 2 points get closer together. I'm doing pseudo math right now. The limit of the secant line as the 2 points get closer and closer together is the tangent line. Well, this is the slope actually. The limit of the slope of the secant line as the 2 points get closer and closer together is equal to the slope of the tangent line. Yeah? You follow me? And so therefore, we can say this thing here. I'm gonna rewrite this. The limit of f of x plus h minus f of x all over h as what? Someone fill in the math. As what's happening? Is x approaching a thing?
X approach h, right?
Well, we have this is x plus h. So in order for this to get closer to this, what's happening to h?
H and
It's
smaller.
disappearing.
H is getting smaller and smaller and smaller. So what is h approaching? As h approaches 0. And so we can't direct substitute. You can't just plug 0 in here because this is divided by 0. But this is the definition of the instantaneous rate of change, which is the slope of the tangent line, which is the derivative. So this thing is instantaneous rate of change, which is slope of the tangent line. This is the derivative of the function f of x. Well, I could do this all day because guess what? So these are all ways to describe what's happening, and the way they write the derivative of f of x is called f prime of x. That's the derivative of f of x, f prime. This is called f prime. It's like Optimus Prime, basically. F prime. Okay. Or they call it the derivative of y with respect to x. dy dx is another way to write that. The derivative of, I should write this. Derivative of y with respect to x. Or I suppose you could say df dx. Right? You could say that. Or stop it. Or sometimes people use ddx as an operator. They say I gotta jump. I gotta come over here. They'll say ddx, which means take the derivative of a thing. ddx, take the derivative of whatever. Right? So it's not far off from this. But ddx means you're going to take the derivative of, and another word for that, it's so ridiculous. Another word for that is differentiate. So the word differentiate means take the derivative of. Differentiate. That's how I spell it anyway. Take the derivative of. So find the instantaneous rate of change of. Find the slope of the tangent line to something. This is so ridiculous. But it is true. There's just different ways to write stuff in math. Andrew.
Like, what's the derivative? Like, what
Good. So the derivative is, so if we take the derivative of this function, we're going to get another function, and that function, the values of the derivative function, the values are the slopes of the original function. Right, you got to think about that for a second. It might hurt your cerebellum a little bit. So you have one function, and you take the derivative, and it gives you a whole different function. And this other function, all of the values along this other function are the slope of this other function that has a changing slope along every point, a variable slope. So the derivative function, it's like a slope function for the original function. It gives you the rate of change of some function along every point on the curve. Hello.
Just one question, like, why is it as h approaches 0? I still don't get that part. Why?
Because this is x, some random point, and this is x plus a little bit.
Yeah.
H is that little bit. And as that little bit gets smaller and smaller and smaller, we're saying x plus a very small number, and eventually these 2 points, just h is getting smaller and smaller and smaller. It's going to 0. Its 2 points are approaching 1 point. Yeah?
Yeah.
Is that okay? How we doing? Woo! Okay, so probably the most common thing you'll see is this. F prime of x is this. If you look in a textbook, you'll see that thing. And actually, sometimes they say, x plus a, or x is approaching a. There's different ways to write this. But it's the same idea. They're using a limit. They're approximating a slope of secant lines and getting closer and closer to a tangent line. And the slope of that tangent line will be the rate of change at this specific point. Because it'll be different here. It'll be different here. It'll be different here. Different here. Woo! So that's conceptually what's happening. We still didn't answer question number 2. Let's go back and actually